We begin the last lesson of this first section of the study of the Introduction to Wave Motion. During this fifth lesson, what we are going to do is to use all the definitions and apply all the characteristics that we have been enunciating in the previous topics. In particular, what I am going to do is to look at two types of wave motion that we are able to detect directly through two of our senses: light waves through our eyes and sound waves through our ears. As far as light waves are concerned, what we have to keep in mind is that light is only a tiny part of the entire electromagnetic spectrum. The electromagnetic spectrum would range from gamma rays to radio waves, but in light waves we are left only in the range of wavelengths from 400 nanometers for blue to 700 nanometers for red. In terms of frequencies, we would go then for the red of the order of 450 times 10 to 12 hertz, and for the violet of the order of 725 times 10 to 12 hertz. The electromagnetic waves have already been enunciated as an example in the waves that are within the classification as non-material waves. Why? Well, because electromagnetic waves can propagate in vacuum. They do not need any material medium to propagate. They can propagate, of course, and what will change will be their propagation speed. They are transverse waves, as we can see in this animation, where the electric and magnetic fields vibrate in perpendicular directions to the direction of propagation of the wave motion. They are traveling waves and three-dimensional. But if we look at the different colors of visible light that we detect, there is no white light. Why? What is white light? Well, the first person who gave an explanation and experimented with white light was the scientist Isaac Newton, who in 1667, in front of the Royal Society, performed the experiment of passing a beam of white light through a prism which was observed by all the members of the Royal Society, because that white beam was decomposed into the different wavelengths of which it was formed. What is the explanation for this? Well, the explanation of this has to do with the fact that the white light is a superposition of all the wavelengths that appear here, in principle, that we are able to see. And what happens is that when the white light reaches the prism, inside the prism, each of the frequencies that are superimposed propagate at a different speed. The frequency is that of each radiation, but the wavelength that we observe are all these that are appearing, that are going to depend on that speed of propagation. The speed of light in a vacuum is about 300,000 kilometers per second. But when we are in a material medium, that speed changes. Precisely the relation between the speed of propagation of the radiation in the vacuum with respect to that speed of propagation in the different material medium is what one of the ways of characterizing those material mediums through their refractive index would give me that proportion. A little bit so that we can see it here live, I have brought this device which is an array of organic LEDs, and each of these LEDs are capable of emitting at different wavelengths. So I can either activate the emission on the red one, which I think looks pretty good, or I can activate emission on the red one. Let's see that we can see it well. On the blue one, and we can see that it will be different. If I activate them with different wavelengths, then if I superimpose the blue one on the red one, notice that we can see it well. We see that we begin to notice some pinkish tones that we do not see, of course, if what I do is simply activate them separately. I can also activate, in this case, the green and orange tones appear. We see how the superposition makes our perception of the frequencies change. Let's turn them all off. This is for the light waves, for the electromagnetic waves in general. Well, and as for the sound waves that we are able to detect through our ears, well, sound waves are material waves. They need a material medium. They need a material medium in order to propagate. They are longitudinal waves, on the other hand, with respect to electromagnetic waves. They are traveling and three-dimensional, and their speed of propagation. in the Earth's atmosphere is 342.2 meters per second. Of course, that speed will depend on the characteristics of the medium, and that speed is when that atmosphere is at 20 degrees centigrade with 50% humidity and at sea level. In general, when we perceive a sound, we do not perceive a pure sound. We do not perceive a sound of a single frequency. In general, it is a superposition of frequencies, but there are instruments such as the tuning fork, where they are capable of emitting a single frequency of about 440 Hz in the case of the tuning fork corresponding to the note A. We humans are able to detect through our ears sounds ranging from about 20 Hz to about 20,000 up to 20,000 Hz, but there are animals such as bats and dolphins that are able to hear ultrasounds beyond the sounds we hear of 20,000 Hz. In particular, the bat, in addition to ultrasounds, is also capable of hearing this band of infrasounds. If we apply all this that we are analyzing to different simple exercises, we will see how we can better understand our environment and even model the events that are occurring by applying all these features. In the first exercise, we are told how far you are from a lightning flash when you measure that the delay between the lightning flash and the thunder is 3 seconds. We have the experience that here can be represented by Jota, who is observing that lightning, and we have to take into account that, of course, the speed of propagation of light that we perceive from the lightning is much greater than that of sound. Therefore, if we take into account that the sound propagates or will propagate at 340 meters per second, and we want to know the space in which the flash, the lightning, is or has been produced, I have to take into account that I am going to calculate that space as the speed times the time. The speed is the 340 meters per second times the 3 seconds that we have taken to detect the sound. Therefore, the lightning has fallen at 1,020 meters, more or less, at 1 kilometer from our point where we are. In the following exercise, we are told that an oceanographic submarine explores the bottom of the sea with an ultrasonic sound that propagates at 1,530 meters per second in the seawater. How far will it be from an island if the sound it emits bounces off the deep wall of the island and is detected again by the submarine 2 seconds after it was emitted? We have to take into account that if you tell me 2 seconds after being emitted, we will have to take 2 seconds to go and return, then in going the distance between the submarine and the island is only in this case of 1 second. The distance in time, that is, the time will only be 1 second. Therefore, if the speed is 1,530 meters per second, in 1 second it will have traveled 1,530. Then the island, we do not need to make any calculation. It is 1,530 meters away. Next exercise, we know that the musical note has a frequency of 440 Hz. If in the air it propagates with a speed of 340 meters per second, and in water, which is a very different material medium, its speed is 1,400 meters per second. I am asked to calculate its wavelength in those two media. I have to take into account that the wavelength will vary because the frequency is the characteristic of the emitting focus. The frequency we have is constant 440 Hz, taking into account that the speed changes the wavelength in the air will be given by the speed in the air divided by its frequency, which in this case will be 340 meters per second divided by 440 Hz, which allows me to obtain the value for the wavelength of 0.773 meters, and in the case of water, as these same calculations give me that the wavelength in water will be 3.18 meters. Let's analyze one last exercise. In this one, what we are going to do is to produce beats in a rope. As Amanda and Jota are experimenting here, she tells me that the end of a rope is shaken with a frequency of 2 Hz and an amplitude of 3 centimeters. If the perturbation propagates with a velocity of 0.5 meters per second, write the expression that represents the movement along the string. To represent this expression, I have to take into account that the periodic movement will have a double periodicity, spatial and temporal. Therefore, we will have to take into account and calculate the parameters that represent that periodicity through the angular frequency, the pulsation that will be 2 pi times the frequency, and this allows me to obtain the pulsation of 4 pi radians per second, And the wave number that will be given by 2 pi times the wavelength. The wavelength that I relate to the frequency and speed, and therefore I obtain for the wave number of 8 pi radians per meter. Therefore, the requested expression is given by this representation of ondulatory movement will be represented by the amplitude and the harmonic function sign of the pulsation by the temporal variable minus, because it will propagate to the right, we will consider the wave number by the spatial variable. Here I have it represented. I can leave it like this, or I can take out the common factor of 4 pi, and it will be represented in this new expression, with which we have seen how to apply all the definitions, all the characteristics of the previous topics in 2 examples of wave motion widely known to us. And also we have already been able to apply it to simple exercises that allow us to know better what is happening in our environment. Thank you very much.